Hey, how's it going, everyone? This is the Solid State Workshop with essential and practical circuit analysis. This is going to be a two-part series on circuit analysis, so put on your thinking cap and let's go. So what exactly is circuit analysis anyway? Well, circuit analysis is a toolkit for understanding and designing more complex circuits. So if you want to get into the world of electronics, or you want to understand electronic circuits, well, you're going to need to understand the concepts brought to you in circuit analysis first. And that's because circuit analysis is a layer of abstraction. It is based off of other abstractions, while other abstractions are built off of it. So you can look at this process chart here of how that works. So you start off in physics, and you learn about the electrons and protons and all the small, low-level things. And then you move on to circuit analysis and learn how that works. And then you move on to electronics, which is based off of circuit analysis. And then you can move on to electronic systems, which is based off electronics. So in order to be successful in each area, you first need to understand the area that precedes it, the layer of abstraction before it. Alright? Cool. What will be covered in this video? Well, a whole range of topics. We're going to start from the very beginning with some simple circuits, and then we're going to move up into the world of more complex circuits. But along the way, we're going to discover methods which simplify the complex circuits and make performing an analysis on them easier. So here are the topics that we're going to talk about today. We're going to start by talking about linear circuit elements, and then we're going to move on to Ohm's law and series and parallel circuits, which you may have already seen before in a physics class or something. Then we're going to talk about voltage and current dividers, then move on to the big two, Kirchhoff's current law and its associated nodal analysis, and Kirchhoff's voltage law and its associated loop analysis. And then we're going to talk about some methods for analysis that are a little more abstract, but are definitely still really cool. And those include source transformation, Thevenin and Norton equivalence, and finally superposition. Today we're going to be dealing with linear circuit elements in all of our examples. And what are the linear circuit elements that we might encounter? Well, we have the humble resistor with units ohm and symbol omega, the capacitor with units farad and symbol F, the inductor with units Henry and symbol H, the voltage source with units volt and symbol V, and the current source with units ampere or amps and symbol A. And now what makes a linear circuit element linear? Well, say we were to write out a relationship between current and voltage for any of these elements, more specifically resistors, capacitors, and inductors. But say we were to write out current as a function of voltage, we would find that the current through these devices, these elements, is going to be a function of voltage times some constant. And so that makes it a linear element, because there is a linear operator in that relationship. In a non-linear circuit element, the operator is something like an exponential operator, e to the power of something. But we won't be encountering non-linear circuit elements today, so don't worry about those. And more specifically, today we're going to be dealing with exclusively resistors, voltage sources, and current sources. Before we go any further, let's discuss the different parts of a circuit and the names we give to these parts. Here's a circuit that we'll use as an example. And now the first part is called a node. And a node is a junction of connecting wires. It's where circuit elements are joined together. So in this case we have 4 nodes, because there are 4 points of connection in this circuit. We have a node connecting the voltage source to a resistor. Here we have 2 resistors and a voltage source connected together, and here we have a voltage source and a resistor connected together. We also include this big node at the bottom. And every point on this big node is at the same electric potential. And well, how could that be? Well, there's nothing in between any of the points on the node here that could alter its potential, such as a resistor or a source. And if, say, we did add one of those things, well, then this whole thing is no longer a node. Maybe only this part would be a node. Next part we have is called a branch. And so a branch is really just a fancy name for any of the circuit elements between two nodes. So here are all our branches in the circuit. It's really as easy as it sounds. It's the element between nodes. I guess the difference between a branch and just a circuit element is that a branch is an element that is part of a circuit by definition, while a circuit element on its own can just be a standalone thing that we can talk about by itself. Alright, so finally let's talk about loops. And a loop is a closed path that begins and ends at the same node. And a loop can't pass through any node more than once. So here we have three different loops in this circuit. We have a small loop here. We have another small loop here. And then we have one big loop that encompasses the entire circuit. And these are all loops. So try to become familiar with these terms because I'll be using them to describe points on a circuit. And plus you get to sound smart when talking to your friends, so that's a plus. Alright, so Ohm's law, the most fundamentally basic and essential relationship in all of circuit analysis. Now before we talk about the actual equation, let's talk about the variables that it is consisted of. So we have V for voltage, I for current, and R for resistance. And now remember, voltage is an across variable, meaning you take the voltage between 2 points or across some element in the circuit. And I, or current, is a through variable, meaning it's the current through an element. And resistance is simply a constant assigned to a particular resistor. Now, Ohm's law says V equals I times R, I equals V over R, or R equals V over I. So it makes it possible for us to solve for an unknown current, voltage, or resistance, granted that we already have two of those elements of that equation. So if we have a circuit that looks like this with a voltage source of 30 volts and a resistance of 75 ohms, we can determine the current that must flow through that resistor. And that's easy because in this case, I equals 30 over 75, and that equals 0.4 amps. Circuit elements can be connected in two basic fashions, either in series or in parallel. So let's talk about series first. In a series circuit, the elements in a circuit are connected one after another, meaning the front of one circuit element is attached to the back of another element, and the front of that element is attached to the back of another element. That's what makes it a series circuit. In a series circuit, there's only one path for current to flow, and that's because there's only one loop here. Where else could the current possibly flow, and how could it possibly be different at different points in the circuit? So we could test for current here, and it'll be the same as current. The same value for current will be found here, and the same value for current will be found here. Now if we have multiple resistors in our circuit, then we can simplify multiple resistors down to one equivalent resistance. And we can do that using a very simple equation that says R equivalent equals R1 plus R2 plus all the way up to Rn, which is the nth resistor. So in our particular instance, we have a 100 ohm resistor and a 50 ohm resistor in series. So the equivalent resistance that would be formed between this point and this point would be 150 ohms. And now that we know the equivalent resistance, basically we can rewrite these two resistors as one resistor. Then we could solve for the current just as we did previously. So applying Ohm's law, we see that the current is equal to 30 volts, the source voltage, over the equivalent resistance of 150 ohms. So dividing 30 by 150 gives us 0.2 amps. In a parallel circuit like this one, all resistors share a common voltage. And we can see that because the 30 volt source here is attached across both the 150 ohm and the 100 ohm resistor simultaneously and in the same places. But the difference between parallel and series is that the currents through each of these resistors can be different, and in this case they are different because the values of the resistances are different. So there's going to be less current flowing through the 150 ohm resistor than in the 100 ohm resistor. And say we wanted to find the current up here, the green current. How could we do that? Well, we can turn these two resistors arranged in the parallel configuration into one equivalent resistor like we did in series circuits. And we're going to use this equation, 1 over R equivalent equals 1 over R1 plus 1 over R2 all the way up to 1 over Rn. And so in this case, we find that the equivalent resistance that will replace this circuit block right here is equal to 1 over 150 plus 1 over 100, and then whatever answer you get there, you just flip it. So this arrangement of resistors can be replaced by 160 ohm resistor. And so therefore we can find what that green current would be. And we're going to just use Ohm's law, and you divide 30 volts by our equivalent resistance of 60 ohms, and we find that the green current would be 0.5 amps. Now say we wanted to find the currents through each of the resistors. How would we do that? Well, we would simply divide the source voltage, since both share the same source voltage, by the resistance. So for the pink current through the 150 ohm resistor, that's equal to 30 volts over 150, which equals 0.2. And the blue current through the 100 ohm resistor is equal to 30 volts over 100 ohms, and that equals 0.3 amps. So some takeaways from here. Basically, we can say that the green current flows into this node here, this junction of components, splits. Some of it goes down one chute, and some of it goes down another chute here. And then back at the bottom, and then down at the bottom, these currents recombine back into the green current, and rinse and repeat. A voltage divider is a circuit that creates a voltage which is some fraction of its voltage source. So here is an example of a voltage divider circuit. It is a series circuit where the output is observed or taken across the second resistor. So in this case, that's that 10 ohm resistor. And it's a series circuit because the 10 volt source and the 40 ohm resistor and the 10 ohm resistor are all in series with each other. We can kind of ignore these wires or lines over here because when we're taking the output, we're just observing the output. We're not really intruding upon the circuit, so it doesn't really contribute to the circuit. At least in the ideal case. We'll see more about that later. But anyway, in a series circuit like this with multiple resistors and a voltage source, or any source, the voltage across each resistor will be different as dictated by Ohm's law, V equals IR. So where I, the current, is the same for all of them, but the resistance will dictate the voltage across each resistor. So if we want to find V out in this case, we're going to first start with finding the equivalent resistance. So that's easy. That's 40 plus 10. So that's 50 ohms. And now we can find the current through these resistors, and that is 0.2 amps. Easy enough. And then to find V out, we can simply multiply the current, which is the same for both resistors because it's series circuit, and multiply it by the resistance of R2. And then in this case, that's 10 ohms. So you just do 0.2 times 10 ohms, and that'll give you the voltage across the 10 ohm resistor. Now, technically, we can also take the voltage across the 40 ohm resistor, and that would be 0.2 amps times 40 ohms, which would give us 8 volts. So as you can see, 2 volts and 8 volts would add up to 10 volts. So that makes sense, I hope. Alright, cool. What we just did is all fine and dandy, except it takes a couple of steps, about 3, to reach our answer. So we want to write a general equation that describes the output of any 2 resistor voltage divider. So here is a general schematic of a voltage divider. So we have a VS, and we have an R1, and we have an R2. And we also have a current that flows through the circuit. It's the same current everywhere in the circuit because this is a series circuit. And we have a voltage output, a V out, which is observed across R2. So let's put all these things into mathematical equations. So R equivalent equals R1 plus R2 because it's a series circuit. And the current I is equal to Vs over R equivalent. And V out is equal to the current through R2 times the resistance of R2. And we know that the current is the same for everywhere in the circuit, so that current through R2 is simply just I. And so now we can substitute in to our V out equation. We can substitute in Vs over R equivalent for I, and then we can rearrange and come to the final equation of Vs times R2 over R1 plus R2, and that will give you the voltage output, the V out, for any 2 resistor voltage divider with any voltage source and any 2 resistors. Now, most generally, we can write an equation that says V out equals Vs times Rx over R equivalent. And what is Rx? Rx is the resistor you would like to find the voltage across, and R equivalent is, again, the total resistance. So we can find the voltage across any of the resistors, and we can have any number of resistors. We can have 3, 4, 5, 6 resistors, and all you have to do is put the value of that resistor in the numerator and over top of the equivalent resistance and multiply it times the source voltage, and you will get the voltage across that resistor Rx. In practice, the output of the voltage divider is going to be hooked up to something. We want V out to do something for us. So in circuits, that means we're going to attach a load to it. But when we attach a load to it, which is in this case a resistor, we fundamentally change the nature of the voltage divider. So let's look at this circuit. This is the new circuit, the new voltage divider, with a load resistor, RL, attached across its output. And RL takes the place of what was before an open circuit. And we're going to learn that attaching a load, RL, reduces the divider's output voltage. And well, how could that be? Well, let's look back to the original equation that says V out equals Vs times R2 over R1 plus R2. And then if we were to look back at the circuit, we would notice that R2 and RL are in what configuration? Well, they're in parallel. So what used to be just R2 is now really R2 parallel RL, the equivalent resistance. So we can rewrite the V out equation to take this into account. So the old R2 now becomes R2 parallel RL, and we can substitute that in anytime we see R2. And we know that based on our knowledge of parallel resistors and parallel circuits in general, that R2 parallel RL is going to be less than the original value of R2. And why is that? Well, think here. If you have R2, which is some value, and then you attach another resistor in parallel with it, you're effectively creating another path for current to flow through. So the equivalent resistance is going to be less because now there is another path for current to travel through. Alright, so if the equivalent resistance up here is less than the original R2, that means that this voltage output is going to be less than the original voltage output. Now, if the load resistance, RL, is much greater than the resistance of R2, then the output voltage only drops by a little bit. And why is that? Well, thinking back to the equation for parallel resistors again, adding a big resistor in parallel with a comparatively small resistor will only reduce the equivalent resistance by a small amount. So this resistance will only be decreased by a small amount. So if this is only decreased by a small amount, then V out is only a little bit smaller than the original V out. Another way to think about this is that the current through RL, the current through the load current, should be much less than the current through the divider, the current through R1 and R2. So if we knew that our load was going to draw 10 milliamps here, then we should ensure as a rule of thumb that the current through R1 and R2 is at least 10 or maybe even 100 times greater than the 10 milliamps flowing through RL. And that's going to ensure that the voltage across RL is close to what we intended it to be. Originally, I wasn't going to include a section on current dividers because most real-world circuits employ voltage dividers and not current dividers. And that's because most sources in the real world more closely resemble voltage sources. However, understanding current dividers is still definitely a good thing to know. So, a current divider is a circuit that creates a current which is some fraction of its current source. So, it's kind of the opposite of a voltage divider, which creates a fraction of its voltage source. And this is what one looks like. This is the general form, the general schematic of a current divider. And a current divider is a parallel circuit where the output current is observed in one of its branches. So in this case, it's the current through the branch consisting of Rx, the current I out going through this branch. And so the first step to finding I out is to first find this value RT. And RT is the equivalent resistance of all the other branches excluding Rx. So it's the equivalent resistance of these two branches and not including the Rx branch. And if there's only one other branch other than Rx, so say R2 wasn't here, then it would simply be the value of R1. That would be the equivalent resistance. But since we have two branches here, we would follow the formula for a parallel circuit for parallel resistances, which is RT equals 1 over R1 plus 1 over R2, and then flipped. Now, to find I out, you're going to follow this equation, which says I out equals IS times RT over Rx plus RT. let's compare this to the voltage divider equation. In the voltage divider equation, what was in the numerator? Can you remember? Right, it was the resistor which we were concerned about, so R2 generally. But in the current divider, it's the opposite. It's the equivalent resistance of everything except for the resistor that we are interested in. And the resistor that we're interested in this case is Rx. And you'll notice that RT is the equivalent resistance of R1 and R2, but not Rx. Interesting. So here we are, the real meat and potatoes of circuit analysis. It's getting good. So Kirchhoff's current law, or KCL for short, says that all currents entering a node must equal all currents exiting a node. Basically, what goes in must come out. And in mathematical terms, the sum of all currents in a node equals 0. We can also express this as a summation of I, and where J is a particular instance of current, just tells you what current we're talking about. And so here's some illustrations to help you understand KCL. The yellow and the green currents represent currents entering a node, while the red, blue, and pink currents represent currents exiting a node. And in the chart below, we can see that the sum of all the currents entering the node equals the sum of the currents exiting the node. Regardless of what the individual currents are, they all add up to the same current. In practice, we write a KCL equation for a node in the form I1 plus I2 plus I3, just like we have in this equation here, and we set that all equal to 0, as we learned before, because the sum of all currents in a node equals 0. And I1 and I2 and I3 are just all the currents coming in and out of the node if you didn't catch on. So we use the convention that a current entering a node is a positive I, because you can think of it as adding to a node, and a current exiting a node is a negative I, because you can think of it as being subtracted from the node. So let's do a problem with this. So we're given a circuit that looks like this, and we're also given some currents initially. So we're given that there's 4 milliamps going to the right, 12 milliamps going up here, and 2 milliamps going to the left. And we're also given the currents I1 and I2 as arbitrarily going to the right, but we're not actually sure if they go to the left or right quite yet. And so we're also set up nodes. So we're going to call this node right here node A, and this node right here in the middle node B. And now we're asked, find I1 and I2 using KCL. And the first thing we should ask ourselves is, do I need to find one current before I can find the other current? So, if I want to find I1, we first need to find the current I2. And if that doesn't make sense, hopefully it'll make sense in a minute or two. So let's write the node equation for node B first, because that's correlated with I2. So the KCL at node B, what is that going to be? Well, here's what it is, and we'll explain why. Well, we have a positive I2 entering the node, so we write positive I2. And we have a positive 12 milliamps also entering the node, so we write positive 12. And we have 4 milliamps exiting the node, so we write minus 4 milliamps. And that's it. And then we set that equal to 0, and then we can easily solve and find that I2 equals negative 8 milliamps. And we'll talk about what a negative current means in a second. So now let's move on to node A over here. So what's the KCL equation at node A? Well, here it is, and we'll talk about that. So we have a negative I1 coming out of the node. Because it's exiting, it's a negative I1. And you have I2 also exiting the node. And then we have a positive 2 milliamps coming up from the bottom here into the node A. So we have a negative I1 minus an I2 plus a 2 milliamps and set that equal to 0. And we know that I2 is negative 8 milliamps, so we can simply plug that right into I2. And we can then solve for I1. And we find that I1 equals 10 milliamps. And so what did that negative 8 milliamps from before mean? The I2 equals negative 8 milliamps. Well, in the direction that we specified, so we just said that, yeah, I2 is going to go to the right. It means that it's actually a positive 8 milliamps going to the left. So all we have to do is, if we get a negative current, is we just say that the real current is going in the opposite direction and is a positive current. So a negative current just tells you to flip the direction of the current and make the value of the current positive. Building off of KCL is something called nodal analysis. And nodal analysis is a process that uses KCL to determine node voltages. And so here's the basic setup for nodal analysis. To use nodal analysis, we first need to create a reference node. And so a reference node in our example circuit diagram over here is the strip of wire on the bottom. That's our reference node. Now, how do we choose which node we want to make our reference node in a circuit? Well, rule of thumb is to pick the node in your circuit with the most connections to it. That'll make your life a little easier. Now remember, in a circuit, a voltage is defined as a difference in potential between 2 points. So if I was to say that the voltage at some point is 5 volts, well, then I also have to specify that it's 5 volts with respect to what other point. So I would have to give that other point. So when we set up a reference node, we're providing that other point in the circuit. We're saying that all of our voltage measurements are referred or referenced to that reference node, so to this node down here. So if we look at our example, what is the voltage at this point right here? Well, it's Vx with reference to ground, or with respect to ground, any way you want to say it. And the voltage here is Vy with respect to ground. Alright, moving on. And so we know that a current through a resistor is described and governed by Ohm's law, which says the difference in potential across a resistor over the resistance gives us the current. So in this case, that's going to be Vx minus Vy over R. And why is it Vx minus Vy? Well, because the current is going in the direction to the right, meaning that there would be a lower voltage at this point than there would be at this point Vx, because a resistor creates a voltage drop. And now Vx and Vy are what we call node voltages. And we might be interested in solving for those. And so to solve for these, we can write the KCL equation for each node in the circuit, except for the reference node here. We exclude the reference node in our equations. And so we can write out the standard KCL equations like we did before in our previous examples, except now instead of writing I1, I2, I3 equals 0, we write in the form Vx minus Vy over R plus Vz minus Vb, whatever, over R, whatever you want, whatever points there are in the circuit. So we use this form Vx minus Vy over R instead of just I. Alright, the moment we've all been waiting for, the nodal analysis sample problem. Oh wait, no one was waiting for it. Alright. Anyway, here is the sample nodal analysis problem that we're going to attempt here. Hopefully I don't get it wrong. We're going to try to find the voltage VO here, the V out, whatever you want to call it. And before we get started, let's note a couple things about the circuit. The reference node is already set up for us, and it's this node down here. How do we know that's the reference node? Because there's a ground symbol attached to it. That basically signifies that it is the reference node. And then we have two nodes up top here that we are interested in. Node 1 here and node 2 here. And we also have two currents that we're interested in. And that's I1, which goes to the right, and I2, which also goes to the right. Those are set arbitrarily. I can have made them go to the left if I had chosen to. Alright, so let's get started, and let's start at node 1. Let's write out the KCL equation at node 1. What's that going to be? Well, we have three currents associated with node 1, and those are I1, I2, and IS. So let's write out the equation for that. Since I1's going into the node, it's a positive I1. Since I2 is coming out of the node, it's a negative I2. And since IS is pointing into the node, it is a positive IS. And now this equation here is just a standard KCL equation. We've done this before. But now to do nodal analysis, we want to put it into the form of a difference in voltage across a resistor over the resistance. And so which ones can we do that for? Well, we can do it for I1 because I1 is associated with the current through R1, and I2 is associated with the current through R2. So we can write this out. We can write those two out in that form. However, we can't write it out like that for IS because IS does not have a resistor associated with it. So here's what that new equation looks like. And we have Vs, which is the source voltage over here, minus V1, which is the voltage at node 1, over the resistance R1. And in a very similar fashion, it's V1 minus V2 over R2. And now, just for instance, why is I2 defined as the voltage V1 minus V2 and not the other way around? Well, because the current is going from left to right. And then IS we just tack on at the end here and set it all equal to 0. And now we can just do some kind of algebraic, clever rearranging, and we can get it into a form like this, where we have V1 times some constant plus V2 times some constant. And usually these constants are the R constants for resistance. And then we're going to set that equal to the other constants that we know here. Alright, so just let that be for now. We have an equation with two variables. So in order to solve for both of those variables, we're going to need another equation so that we can get two equations, two variables, and then solve using some method. So let's move on to KCL at node 2. And the KCL at node 2 is kind of weird, but it will hopefully make sense. So KCL node 2 is I2 minus I2 equals 0. And you might be saying, well that's weird. I don't know why you're writing that out. But bear with me. So because there's two currents associated with node 2. We have the current flowing into I2 from here, and the current coming out of I2 down to the reference node. And those currents are in magnitude the same, but we can define them differently. So what do I mean by that? Well, the current going through R2 here is technically V1 minus V2 over the resistance R2. And because no current can flow anywhere else, that same current also flows through R3, so that's why they're the same. But the current through R3 can be defined as V2 minus 0 for ground over the resistance value of R3. So that's where this comes from. So yes, they are the same current, but we can define the current through each one of these resistors, which are participating in this KCl equation differently. Alright, so now again we can do some rearranging like we did before and land on an equation like this. So now we have two equations and two variables, and that means we can solve for it with some method of our choosing. For me, I'm going to put it in matrix form. And so here's what the matrix form is for these two equations. So we have a 2x2 matrix here, which includes all of our R variables. And here's our matrix for V1 and V2, which we're trying to solve for. And here are some of our constants in this matrix. And then, however you want to solve for this is up to you. You can use system of equations, you can plug things in. Whatever is most comfortable for you is what you should use. For me, I can pump this into my calculator pretty easily, so that's probably what I'll do. I would do the inverse of this matrix times this matrix, and that should give me V1 and V2 pretty easily. And so let's just, before I get ahead of myself here, we can rewrite this matrix with real numbers. So I've converted all the R1s and R2s and R3s into real numbers here. And I've converted this expression into a real number over here. And so I can solve for it. And so I find that V1 equals 14 volts and V2 equals 6 volts. And because V2 and V out here are the same point electrically because they're on the same node, it means that V2 equals VO, or V out, and so V out equals 6 volts across here. Well, that's kind of a lot of work, so I'd be lying to tell you that this was the easiest way you could have done this problem. So bear with me, and we'll now look at an easier way to do this. So I just blew through that last example at like Mach 3, and I don't know if that made it seem easy or if I just confused you. Hopefully I didn't confuse you. But the way we did that problem was not very smart. We kind of went into it blindly in a brute force method. We just kind of collected as much data as we could and then prayed that we could find an answer based off that data. So let's try to be a little smarter about it, and we'll do that in this method. Again, let's start with a KCl at node 1. So the KCl node 1 is going to be the same I1 minus I2 plus IS, and you should know why we have negatives and positives there. And as we start expanding it out into the nodal analysis form, the beginning, it starts off the same. Vs minus V1 over R1, which corresponds to the current I1 here. But now I2 we define as V1 over R2 plus R3. Why did we do that? Well, it's because we lumped together R2 and R3 as one resistor, because they are in series, as we learned before. And we can disregard this whole wire kind of flying off here, because there's no current in that wire. It's not going anywhere. It's not doing anything. So you can completely disregard that wire and just call this a series connection of R2 and R3. And now, what is the voltage across R2 plus R3? Well, it's the voltage at node 1 up here, V1. So it's V1 with reference to ground is the voltage across R2 plus R3. So that's why we have that term there. And IS is simply just tacked on the end like we did before, because we have no other way of defining it. Alright, so now what we can do is we can split up all our fractions and move things over to other sides of the equation, and we get all our V1s on one side of the equation and our constants on the other side of the equation. And now we can plug in for R1, R2, and R3, Vs and Is, and we can find V1 just like that. So we found the voltage at this node is 14 volts, of course with respect to ground. And so now how can we find the voltage at V2? if we have the voltage up here, and we have these two resistors in series, how could we do? Of course, we're going to use the voltage divider equation, because this is a voltage divider. We have two resistors in series. We can pluck off the voltage across that second resistor by using the voltage divider equation. So that is super simple. And all we have to do is say that V2 equals the source voltage, or so-called source voltage. In this case, it's V1 here times the resistor of interest, R3, over the combination of R2, R3. So V1 times R3 over R2 plus R3. And we simply solve for that. And we find that V2 equals 6 volts. And we know that V2 is the same thing as V out. And now those are the same answers that we got before, and it took a lot less work to get to those two answers. So use your head when you're doing these problems. Try to pick out these circuit elements, these circuit blocks, like voltage dividers. Voltage dividers come up everywhere. So look for those first. Look for things like that. It'll make your life a whole lot easier. Kirchhoff's voltage law is the complement of his current law. And it states that all voltage drops must equal all voltage rises in a closed loop. And well, what does that mean? So, imagine that you're going to go skiing. You can imagine a voltage rise as a ski lift that carries you to the top of a mountain. And as you get higher on your journey to the top of the mountain, your potential energy, like you know from physics, also increases. Your potential increases. So that's a voltage rise. And then once you get to the top of the mountain, you're up at the top, yay, you're going to start skiing down. And skiing down the mountain is like passing through resistors in a circuit. That's one resistor right there. And then you get to this flat point. You can think of that as a node, even though that really wouldn't be flat. But just for the sake of this argument. And then the next hill is like another resistor. And then you hit some flat point. And then the next hill is like another resistor. Well, let's think back about skiing again. So as you ski down your first hill right here, and you get to this flat point, you're at a lower potential than you were before up here. So you've experienced a potential drop. And same thing goes for here. You're at a lower potential at this second flat section than you were at the first flat section right here. So you experience another potential drop. And eventually you get to the bottom where you experience one more potential drop. And so you notice that once you've reached the end, here you've reached the same potential that you started at the very beginning before you even started your ascent up the hill over here. You're at the same potential of 0. And so if you're an electron in a circuit, and these were all resistors, and this was a voltage source which kind of energizes you, then if you're an electron, you would, after you finish your descent, you would get immediately back on the lift and start all over again, because it's an electric circuit and it keeps going, right? Alright, so maybe that was kind of a weird example. Here's the circuit I was trying to model using the skiing analogy. So we have the voltage source here, which is the voltage rise, and then we have 3 resistors in series, and those would have been the 3 little hills, and those are all voltage drops, because if we have a current going in this direction, then they're all going to be voltage drops, and then this will be a voltage rise through the voltage source. So we said that the drops must equal the rises, right? That is, the sum of all voltages in a closed loop equals 0. That's another way of saying that. And once again, we can express this in the summation notation. That rhymed. as the summation of all the V's equal to 0. And again, J just tells you what voltage we're talking about. So voltage V1, V2, V3, whatever one we're talking about. And now before we wrote out an equation for each node and its associated currents, that was in KCL, but now we're dealing with KVL, and so we're going to write out an equation for each loop and all the voltages associated with that loop. So we write that out in the form V1 plus V2 plus V3 and on up to Vn, and set that equal to 0, and that's how we write an equation for a loop, and that is a KVL equation. Alright, just to clarify a few things, say we have like a single loop circuit like this one. The first thing we want to do is set up some arbitrary loop current. In this case, it's called I right here. And usually we set up I to go in the clockwise direction. And if we had multiple loops in our circuit, they'd all go in the clockwise direction. And that just helps to simplify the problem. So set them all up in the clockwise direction. And now, if we were to go through a voltage source from negative to positive, as we would since we're going in the clockwise direction, then we are experiencing a voltage rise. And interestingly enough, a voltage rise in a KVL equation by convention is actually a minus V. It's kind of weird. So in the KVL equation, this would be minus V1. And now, if we had a voltage source, say in the same place here, except we had the positive and the negative switched, and we went through that voltage source from positive to negative, then we would have a voltage drop. And in a KVL equation, a voltage drop is a positive V. And then as we keep going along and we go through all these resistors right here, all these resistors will have a voltage drop because they are resistors, and resistors always have voltage drops, and that's a plus V. Alright, let's do a problem. Okay, here's our example circuit, and we're asked to find VAB across this 2 ohm resistor using KVL. So the first thing that we should do is to find the current around the loop. So the current that goes around this loop. And the current will be the same everywhere because everything is in series with each other. So every point in the circuit will have the same current. So to do KVL, we need to set up our arbitrary loop current in the clockwise direction. So we call I that loop current. And then we want to start at some point in the circuit and perform KVL by going through each one of the elements in the loop and doing that until we return back to that point where we started. So for this circuit, we're going to start at point B down here. And we're going to go through all the elements in the clockwise direction and add up all of their voltages until we get back to B. And here is what the KVL equation would look like, and we'll explain why. So we start at B and we go clockwise. We're going to go through a voltage source from positive to negative. That means it's a voltage drop, so you write a positive 15 in the equation. And then we get to this 3 ohm resistor right here, and we don't really know the voltage across it, but we do know that there is a current I going through that resistor. So V equals IR as per Ohm's law, so you can just simply write plus 3 times I. Since it's a voltage drop, it's a positive 3I. And then you go through that, and then you come to this 1 ohm resistor, and it's also going to be a voltage drop because it's a resistor, and it's 1 ohm times the current I, so 1I. And then you get up to this 6 volt source, and you're going to go from negative to positive on your 6 volt source, so that's in fact a voltage rise. So you write a negative 6 in your KVL equation. And then you come to the 3 ohm resistor and do like you did before and do 3i plus 3i. And then you come to your 2 ohm resistor and do plus 2i. And then you return back to your starting point B. And once you've reached your starting point, you know you've completed the KVL equation. So now what we can do is combine all our like terms, and we can solve for our current. And so we see here that the current I equals -1 amp. And what does -1 amp mean? It means it's actually 1 amp in the opposite direction that we specified. So yeah, it is in fact in the other direction. So now we want to find VAB. How can we find VAB? Well, of course, very easily. We know that V equals IR, and so we just multiply the current times the resistance in which AB is across, and AB is across this 2 ohm resistor here. So we do VAB equals -1 amps times 2 ohms, and we get that VAB would be -2 volts from A to B, which is the same thing as a +2 volts from B to A. So, loop analysis with KVL. It's kind of the parallel to nodal analysis with KCL. Loop analysis is a process that uses KVL to determine loop currents. So here's the example circuit that we're going to look at. So if we have a circuit like this, the first thing we want to do is to assign loop currents to all the independent loops. And in this case, we have 2 independent loops, and they are these smaller sub-loops within inside the circuit. Those are independent loops. And when you see a problem that should be solved with loop analysis, it'll be pretty obvious what are the loops. There'll usually be like 2 or 3 of them. Maybe 4 if you're lucky. So what we want to do is assign the loop currents to both of these. So we'll call them I1 and I2, and they'll both be in the clockwise direction. And that's because that makes life easier. All about making life easier here, you know. Alright, so to solve for these loop currents, we want to write a KVL equation for each of them, and then solve using system of equations or matrices or whatever floats our boat. Alright, so now a couple words of wisdom, even though I'm not that wise, but a couple words of wisdom about solving these. If we're in loop 1 with current I1, then say we're to go through this middle resistor here. What's the value of the voltage across that resistor? Well, you would initially say, well, it's R times I1, right? Close, but look, I2 is also passing through that resistor. We're not in I2, but I2 has to be considered. So what is the voltage across this resistor? Well, it's the resistance value R times I1, which is in the positive direction, because we're going in the positive direction of I, minus I2, because I2 is going in the opposite direction of I1. So I1 is in the positive direction, so we have a positive I1 minus I2 because it's going in the opposite direction of I1. So R times I1 minus I2 is the voltage across this resistor. And now say we were in the I2 loop. It would be basically the opposite. I2 is now in the positive direction because we're going around the loop like this. And now I1 is going in the opposite direction because I1 is going down through that resistor and I2 is going up through that resistor. And we're going to say that I2 is in the positive direction because that's the loop that we're in. So R times I2 minus I1 for that particular loop. Hope that makes sense. Alright, so let's work on this circuit using loop analysis. We're asked to find the current I1 through this 1K resistor. And we're going to set up 3 different loop currents because we have 3 independent loops in this circuit. So we're going to set up an I1, an I2, and an I3 loop. And so let's start up in I1 and write the KVL equation for that. So the KVL for I1, here it is. And how did we get there? Well, say we started in the lower right-hand corner of the I1 loop, right here, and we went in the clockwise direction as per I1 is in. What would we get? Well, we go through this voltage source from negative to positive, so therefore we have a negative 15 as per the convention. And then after we get the negative 15, we come across this 2K resistor right here. And what is the voltage across this 2K resistor? Well, it's going to be the current through the 2K resistor times 2K, the resistance of the resistor. So what is the current through that 2K resistor? Well, it's obviously going to include I1 because we are in the I1 loop. But what other current is associated with it? Well, also I2, right? Because I2 is going through that 2K resistor also. Now, what direction are we in? Well, we're in the direction of I1. So I1 is going to be positive, and I2 is going in the opposite direction of I1, so it's going to be negative. So how would we write this? Well, just look up here, 2K times the quantity, I1 minus I2. And so I1 is going from right to left, and I2 is going from left to right. And so that's kind of justification for why we can write I1 minus I2. They're going in opposite directions. Alright, so after we're done with the 2K resistor, we keep going up in our loop. And nothing there, and we come across the 1K resistor. What is the voltage across the 1K resistor? Well, it's going to be the current through the 1K resistor multiplied by its resistance. So what's the current through this 1K resistor? Well, it's simply just I1. It is the only associated current with this 1K resistor. So the voltage is simply 1K times I1. And then we keep going, and we get back to our original starting point. So we know we've finished. And so we finish off our equation by setting it equal to 0. And so now a good next step for us is to look at these resistance coefficients here of 2K and 1K and find the greatest common factor between the two of them and then divide by that. So in this case, we're going to divide by a 1K. So let's divide everything in this equation by 1K and then simplify further. So here's what we get. Now, how did we go from a 15 over 1K, a negative 15 over 1K to negative 15 milliamps? Well, if you remember, if you divide something in volts, which 15 is in, negative 15 is in, by something in kiloohms, you will get something in milliamps. Maybe something good to remember. Makes your life easier. Now, 2K and 1K are going to cancel to just a 2, and 1K and 1K are going to cancel to a 1. And of course, 0 divided by 1K is going to be 0. Alright, so now we can simplify this a little more and come across our final equation for the KVL for the loop I1. So we have 2 variables and 1 equation, so we're going to need at least 1 more equation to solve for both of those variables. So let's move on to the KVL for I2, and we're going to follow a very similar process to find our KVL for I2. So let's start in the same place that we kind of started in I1. We'll start in this lower right hand corner and we'll move clockwise. So what's the equation going to be? So here it is. And how do we get there? So if we're in our loop and we move clockwise, the first thing we come upon is the 2K resistor. What's the voltage across this 2K resistor? Well, it's simply going to be, again, the current through that resistor times its resistance. So what's the current going through that resistor? Well, it's only going to be I2. There's no other associated currents. Nothing else is flowing through the 2K resistor. So the voltage is simply 2K times I2, as we have here. And then we keep going clockwise around the loop, and we come across the second 2K resistor. And now the voltage across this 2K resistor is going to be basically the opposite of what we found in the I1 loop when we were in an I1 loop. So up here, remember, we found that the voltage across that same resistor was 2K times I1 minus I2, the quantity of. But now we're going to find that the voltage in this loop is going to be 2K times I2 minus I1, which is basically the opposite. And so why is that? Well, now remember that we're in the direction of I2. I2 is our positive direction. So it's going to be a positive I2. And I1 opposes I2. It's in the opposite direction. So we're going to have a negative I1. Because I2 is going from left to right. And I1 is going from right to left. So that's why we have a positive and a negative. Alright, so then after the 2K resistor, we hook a right here, and we meet up with our 4K resistor. So what's the voltage across the 4K resistor going to be? Well, again, it's going to be the same thing. Its resistance times the current through it. So we're in the loop I2, so that takes the positive direction. I2 is in the positive direction, so I2 is positive again. And now we have I3 also going through that 4K resistor, and I3 is in the opposite direction of I2, so we write a negative I3. And after we were done with that resistor, we come back to where we started. So we know we've finished. So our equation equal to 0, and let's do a similar process to what we did in I1. So what are we going to do? Well, find the greatest common factor of all the resistances, which in this case is going to be 2K, and divide everything by 2K. And so a little more simplification, and we land upon something like this. So how do we get this 5 milliamps? How did that sneak in there? Well, look at our I3 loop over here. What is in our I3 loop? We have a current source, a 5 milliamp current source. So whenever you have a current source in one of your independent loops, the value of the loop current, I3 right here, will automatically take on the value of the current source. So actually in this case, I3 is going to be a negative 5 milliamps. And why is that? Well, you guessed it, it's because the 5 milliamp source is going in the counterclockwise direction, and I3 is in the clockwise direction. So to account for that, we make I3 a negative 5 milliamps because it's going in the opposite direction of I3, of the 5 milliamp source. So that's why when we have an I3 right here, it's a negative I3. You plug in a negative 5 milliamps and a negative, make a positive, and that's why we get positive 5 milliamps right here. Set that equal to 0, and let's continue our simplification process, and we come across our final equation for the KVL for I2. And now we have two equations, two variables. We're good to go. Let's solve for I1 and I2. And well, actually right now we're just going to solve for I1 because that's the only thing we're interested in. Okay, so we can use whatever method we like the best. I'm going to use some simple system of equations and land upon I1, hopefully. Alright, so we take the first equation from I1 right here, and we're going to multiply it by 2 so that the I2's right here go away. I'm sorry, I mean multiply this by 2 so that the I2's go away. Negative 4 plus a positive 4 I2 is going to be, of course, 0 I2, and then just continue adding everything here as you know how to do, I'm sure. So we get 5I1 equals 20 milliamps. So of course I1 equals 4 milliamps, and that is our answer. So the current through this 1K resistor is going to be 4 milliamps. And that's how you do it using loop analysis. Alright, so we're on the home stretch now. And I promise that the rest of the video won't be too painful. So now let's talk about something called source transformation. And before we can do that, let's get some definitions out of the way. So, first thing is called a Thevenin circuit. What's a Thevenin circuit? Well, a Thevenin circuit is just a circuit that takes on this form. So that's a voltage source in series with a resistor. And the second thing is a Norton circuit. And a Norton circuit takes on this form. It's a current source in parallel with a resistor. And so this slide is titled Source Transformation. So what's that? Well, source transformation is a method that allows us to easily convert between these two types of circuits. So that means if I have a Thevenin circuit, I can create a Norton circuit which will behave identically in a circuit. So what's the conversion process? Well, the first part is super easy. The resistor for both of them is the same. So R Thevenin and R Norton are the same value. So from now on, we can just refer to the resistance as R because they're the same. And so if I have a Norton circuit, you can find the equivalent Thevenin voltage by using Ohm's law and multiplying the Norton current, I know, by the resistance. And that would give you the equivalent Thevenin voltage. And if you have a Thevenin circuit, you can find the equivalent Norton current by dividing V Thevenin by R. And it's literally that easy. And that's how you can do source transformation, turning a Thevenin circuit like this into a Norton circuit like this, and vice versa. It can really help you simplify down circuits and make them easier for you to analyze using the methods that we've already learned. So, Mr. Thevenin and Mr. Norton both created theorems that say very similar things. Basically, they say you can take any black box circuit consisting of voltage sources, current sources, and resistors, and can convert them into a Thevenin circuit or a Norton circuit. And a black box is basically just some system or some circuit where you don't really care about the actual components inside of it. You may know the components and you may know the schematic for the black box circuit, but you don't really care about them because all you care about is how the black box interacts with the outside world. What are its inputs and outputs like? So you can reduce a super complex circuit to just one source and one resistor. And that's all you need to describe the behavior of one of these circuits. And as we just learned about source transformation, you can convert this black box circuit into, say, a Thevenin equivalent circuit. And then once you have it in the form of a Thevenin equivalent circuit, you can easily convert it to a Norton equivalent circuit. And of course, you can do it the other way around. You can convert first to a Norton equivalent circuit, and then you can convert to a Thevenin equivalent circuit. So it's really up to you. To find the Thevenin or Norton equivalent circuit, one of the things we need to find is the value of resistor R. And so for what we're doing, we're going to be presented with some multi-element circuit, and we're going to be asked to reduce it down to its equivalent. So how do we find R? The first thing we want to do is to detach the load resistor, if there's one present. And how do you identify the load resistor? Well, it's the resistor the output voltage is being taken across, or the output current is going through. Next thing to do is to set all sources equal to 0. That means you're going to short circuit all the voltage sources and you're going to open circuit the current sources. And why does this set them equal to 0? Well, remember that a voltage is a difference in potential between 2 points in a circuit. And that's what a voltage source creates, a difference in potential. And so if you were to connect those 2 points together, as you do in a short circuit, there's no longer any potential difference. Therefore, the voltage is 0. And in a current source, by open circuiting in it, you prevent the possibility of any current flowing. So therefore, there's 0 current. And so that's how you set sources equal to 0. And that's why. And lastly, you want to find the equivalent resistance of this new circuit looking in, quote unquote, looking in from the two output terminals. and you can use your knowledge of series and parallel resistors and combinations of series and parallel to simplify down to just one resistor. Let's just hone in on Thevenin equivalent circuits for now. We'll get to Norton equivalent circuits a little later, but for now we need to find the second part of our Thevenin equivalent circuit. We've already found R. Now we need to find V Thevenin. So what are we going to do? Well, here's our known circuit, just for example, and the resistor in purple over here represents the load resistor. So what's the first step? The first thing we want to do is to detach the load resistor, again, as we've done before in the previous step, finding R. And the second step is to find the open circuit voltage, VOC, across the circuit's output terminals. So it's really as simple as that. Now, that process can be pretty complicated because you might have to use nodal, loop, voltage divider, source transformation, any of those processes to find VOC. But that's really all you have to do. You just have to detach the load resistor and then find what the voltage across the output terminals would be. And this includes all the sources, of course. The sources are not set equal to 0 when you're finding V Thevenin. As usual, let's do an example to really understand what we just learned. So we have a circuit, and we're asked, find VAB, the voltage across these two output terminals, using Thevenin's theorem. So what's the first thing that we're going to do? Well, let's find R Thevenin, or just R, whatever one you want to call it. So here's how we find R Thevenin. In this new circuit over here, well, what have we done? Well, we've removed the load resistor of 6K, and that's the load resistor because AB is across it. And then we've short-circuited our 3-volt voltage source, and we've open-circuited our 2 milliamp current source. And now all we have to do is find the equivalent resistance of this new circuit looking in from these terminals. So we get an equivalent resistance of 3 kiloohms. Easy. Now the next part is going to be a little more difficult, but it's going to be finding V Thevenin. So what are we going to do? Well, here's a circuit we're going to work on. We've moved this circuit down here, and we've removed the 6 kiloohm load resistor. And I've labeled this as node 1, and the voltage at node 1 being V1. So there's a bunch of different ways you could do this to solve for VOC, but here's the way I'm going to do it. Let's do the KCL at node 1. So we have 2 milliamps going into the node, and we can't have a current here because this end is disconnected. So we can only have a current through the 2K and the 1K, like so. So the KCL is simply going to be 2K into the node, and then out of the node comes a current of V1, since that's the voltage here, over the equivalent resistance of 2K plus 1K, which is 3K, and then and set that equal to 0, because those are the only two currents. And then we can simplify, and we get that the voltage at V1 is 6 volts. So basically you can think of it as a 6 volt current voltage source between here and here. So now how can we find VOC? Let's try a KVL, and we can do a KVL on this loop right here. Even though VOC is totally an open circuit, you can still do a KVL on it. You can create a loop that includes that voltage. So here's how the loop turns out. And how do we get a negative 6 volts? Well, remember, if this is technically a voltage source between here and here, you're going to go through the negative to the positive here of that voltage source. So that would be negative 6 volts. And then you get a negative 3 volts going through the voltage source here. And then you get a positive VOC going through the voltage source, and then you've returned back to where you started. So that's how we get that KVL. And then you can simplify and add, and you get that V Thevenin, which is the same thing as VOC, equals 9 volts. But we're not done, because we just found VOC, or we found V Thevenin, and we found R Thevenin, but now we need to find VAB, which is the voltage across this 6K resistor right here. So let's move on to the right over here. And this is our circuit now including the load resistor, because we can't just disregard that load resistor. It's still part of the circuit. Here's our equivalent, our Thevenin equivalent circuit. It includes the 9-volt source right here and the 3K resistor in series. And then we add in the 6K load resistor. So we're asked to find the voltage across that 6K load resistor. And well, how can we do that? Well, it should be obvious by now. We're going to use a voltage divider. And that's real easy because all you have to do is multiply that source voltage of 9 volts by the R2 over R1 plus R2 combination. And that's going to be a VAB of 6 volts. So as you can see, kind of a lot less work than doing it in a more traditional manner, but we still get to the same result, and we can probably do it quicker. Norton equivalent circuits. So to find I Norton, which is the parallel to V Thevenin, we follow a very similar process with some small changes. So we have a known circuit, and again, the first step we're going to do is to detach the load resistor, just as we did before. And now the second step is to short circuit the output terminal. So we didn't do this before. Before we had an open circuit, but now we're going to short circuit the output terminals, meaning we take a piece of wire and directly connect those two terminals together. And the third step is to find the short circuit current ISC through the shorted output. So the current through that piece of wire that we just put in there. Whereas before we found the open circuit voltage between those two terminals, now we're finding the short circuit current. And now you can use, again, any form analysis to find that short circuit current, nodal, loop, voltage divider, whatever is the quickest and the easiest, or whatever you understand the best. Let's do the same problem we did before using Thevenin's theorem, and now let's use Norton's theorem. So here's the circuit from before, and we're asked to find VAB, and now we're going to use Norton's theorem to find VAB. How is the process going to be similar, and how is it going to be different? Well, the first part, finding R Norton or R Thevenin, the same thing, is going to be identical. So we just short circuit our voltage sources, open circuit our current sources, and remove the load resistor, and find the equivalent resistance. And that's what we did here. 3 kilo ohms, same as before. And now we have to find I Norton. So how do we do that? Well, I redrew the circuit down here, except now I removed the 6 kilo ohm load resistor, and I've short circuited the output. Next thing I'm going to do is just for me visualizing, I've moved the voltage source over there, just so I could see a little better. You don't have to do that, personal taste. And now, what do we have here? Well, we have a current source in parallel with a resistor. What can we do with a current source in parallel with a resistor that we just learned? Of course, we can do source transformation on it and make it a voltage source in series with a resistor. And that's what we did here. So we had a 2 milliamp current source in parallel with a 3K resistor. To find the V Thevenin of that, you just have to multiply 2 milliamps times 3K and you get 6 volts. And now you put that 3K resistor and you put it in series with that new 6 volt voltage source. And now we have a 1 loop circuit with 2 voltage sources and 1 resistor. What could be easier? And what we want to find is the current through that loop, because the current in that loop is going to be ISC, and that's what we're interested in. So let's do the KVL on that circuit. So let's start up here on the top, on the upper right, and we go through the 3 volt source, so that's going to be a -3. Come around here, go through the 6 volt source, and that's going to be a -6, and we come across this resistor. And what's the voltage across this resistor? You guessed it, it's 3K times the current ISC. And we set that equal to 0 because we know we're finished. And so we can reduce and simplify, and we get that ISC equals 3 milliamps. So that is our short circuit current, 3 milliamps. And that's also equal to I Norton. So now let's rewrite our circuit in its Norton form. And now we can solve for VAB. So here it is. We have our 3 milliamp source, which we just determined was 3 milliamps, in parallel with the 3K resistor. And now, again, as we did before, we're going to tack on that 6K load resistor right here, because that has to be included in our analysis to find VAB. And now how can we find the voltage across AB? Real easy. Find the equivalent resistance of the 3K and the 6K in parallel, which turns out to be 2K, and then do V equals IR, and that is going to be 3 milliamps times the 2 kilo ohm resistor, the equivalent resistance between 3K and 6K, which is 2K, so 2K times 3 milliamps, and we get 6 volts across AB, just as we got before using Thevenin's theorem, and now we've just used Norton's theorem to find the same answer. So it's really up to you. Which one do you like better? And use whatever one makes more sense for you. Alright, so there's light at the end of the tunnel now. Thank you for sticking with me. We're almost done. The last topic for today is superposition theorem, and it's really a clever theorem. So in a circuit, you can think about voltage sources and current sources as driving forces, each which contribute to the circuit in some way. So superposition basically says you can consider the circuit one source at a time, find each source's contribution to the circuit, and then add up all those contributions at the end. And that will be the actual contribution. So here's the general process for doing that. Superposition says that a circuit with multiple sources can be solved by this process. First thing we want to do, set all sources equal to 0 except for the one that we're considering. And we know how to set all sources equal to 0. Then you want to solve for the necessary currents and voltages, depends on the problem, of course, using only that one source, which is actually going to be relatively easy. And then you want to repeat step 2 with the next source, and then the next source, and however many sources you have. And then at the end you want to, quote, superimpose the solutions onto each other, basically the sum of all of the solutions. Now you're going to have a bunch of different equations with seemingly the same variable. It's going to be like, you know, I1 and I2 or whatever. But you need to differentiate between the variables from the different equations because they're not the same. So what you want to use is the prime symbol to differentiate variables with the same name. So here's the general process. We have a circuit that looks like this, one of these double loop circuits, classic, right? And here's what we're going to do. We're going to take out one source. So in this case right here, we've taken out this voltage source, and we're going to solve for I1 single prime and I2 single prime. And then we've, in the right circuit over here, we've taken out this voltage source. And we solve for I1 double prime and I2 double prime. And then, at the end, the big finale, to actually find the real value of I1, all you do is add up I1 single prime plus I1 double prime, and you get the actual value for I1. Same thing for I2. So that's the process. Now, of course, let's do one last example. Last hoorah. Alright, last problem for the day. Let's try to find VO, the voltage across this 6K resistor, using superposition. So what's the first thing that we're going to do? Well, we're going to draw the circuit with one of the sources removed. And the first source we're going to remove is the 12 volt source. So that's going to get short circuited. So that's what happens here. And now you're probably wondering, whoa, where did these two 6K resistors go? Remember, now if I short circuit this 12 volt source, what am I also short circuiting? I'm also short circuiting these two 6K resistors. So they are also short circuited. So they go away, and you just replace this entire circuit block right here with one short circuit, which is what you see right here. And now we're interested in solving for VO single prime right there. What have I done to help us out a little bit? I put in a current I1. And so what type of circuit are we looking at right here? Well, we're looking at a classic current divider. And how are we looking at a current divider? Because we have a current source, and these two branches right here, they're in parallel. So that's a classic example of a current divider. So if you can think back to the equation of a current divider, we're going to find that I1 is defined like this. And it's equal to everything that we're not interested over the total resistance times the current source. And that's what we have here. So we're interested in the current I1, which is going through that one 6K resistor. So what we put up top is the two 6K resistors in series. That's the equivalent resistance of that branch. And then you put it over the equivalent total, and that's 6K plus 6K plus 6K. And then multiply that by the value of the current source, and you get the current I1. Lovely. So simplify that down, you find that I1 equals 4 milliamps. Now how do we find VO single prime? Well, easy. V equals IR. But now you just have to take into account that I1 is flowing from negative to positive of VO single prime, so that we basically just flip the voltage. So it's a negative 24 volts. Negative 4 times 6 equals negative 24 volts. So that's VO single prime. Now we have to find VO double prime. And so how are you going to do that? Well, we're going to take the original circuit, and instead of deleting the voltage source, now we're going to delete the current source. So let's draw that out. So it's going to look like that. So we have an open circuit where the current source used to be, and now we call this voltage VO double prime. And I've grayed out these two 6K resistors. I mean, these two 6K resistors really have some bad luck. Why'd I gray those out? Well, if I have a single loop here, you have to, if you really notice right here, you have a single loop right here. What happens in this loop has no bearing on what happens in this loop. So we're just going to disregard whatever happens in that loop. Treat this as a single loop. And if I want to find the voltage across this 6K resistor, what can I do? Well, I can do a number of things. I can do KVL, or probably something else. But right now, I'm going to use voltage divider. I'm really into using my dividers right now. So how do I use voltage divider? Well, I just do my source voltage of 12 volts times the resistor that I'm interested in, which is this 6K resistor. But it would be the same actually for any of them, over my equivalent resistance of all the resistors. So that's 6K plus 6K plus 6K, and that'll give me the voltage across that 6K resistor, the voltage VO double prime, and that equals 4 volts. So I've just calculated that VO single prime equals negative 24 volts and VO double prime equals 4 volts. How do I find out the real value of VO? Real easy. All you have to do is add the two together. VO single prime plus VO double prime equals VO. And so, of course, that is going to equal negative 20 volts. Real easy. And it was pretty quick. All right. Great work. Here are my ending remarks for this video. First thing, the key to solving circuit problems quickly and correctly is practice. By far the most important thing you can do is keep practicing. Second thing, each technique that we've learned today is not terribly difficult on its own. The challenging part is really identifying which technique or combination of techniques is appropriate for a given circuit. So someone can ask you, solve for this current using this technique, and it'll probably be pretty easy because you're going to know exactly what you have to do. But if someone just says solve for this current and they don't tell you what technique to use, that's where the challenge lies. And it's really important to be able to identify which technique makes the most sense. Third thing, experiment with circuits on your own. Can't stress this enough. Play around with circuits and see how changing things in a circuit will affect it. And you can purchase the components that we used in this video. Even though we didn't use real components, we just put them up on a screen, but you can purchase the real components from distributors like Mouser and DigiKey, and they're pretty inexpensive, probably only a couple cents each for those resistors. And you can create a voltage source using batteries, or if you have a power supply, that's even better. And you can see how changing things around will affect the circuit. In a similar way, you can use simulation software like LT-Spice, which is free, and you can download from Linear Technology's website to verify your findings and to learn more about circuit behavior. So if you have homework to do, or if you're just analyzing some circuit and you want to make sure you did it right, you can put it in LT-Spice and check if your answers match. And of course, you can always play around and see how changing values will change your circuit. Alright, so I really encourage you to do those things. And keep practicing, and I'm sure you'll be great at circuit analysis. As always, thanks for watching. I know my videos are long, and if you sat through this whole thing, thanks so much. But I hope it was helpful for you. I'd love to hear your feedback if you have any. What would you like to see more of? What did you not enjoy so much? I'd like to hear that too. And if you liked it, give it a thumbs up. And if you want to see more videos, definitely subscribe to my channel. Alright guys, have a great day.